with Juno on a trek to Jupiter, a planetary piece of the puzzle on the beginning of our solar system. Your roll program is affirmative.
Greetings, Kerbonauts. This is Kerbal Space Program. I'm Bob Fitch, and this is the third and final installment of the mini-series for Juno going to Jupiter in real solar system. In the first two parts, we launched the Juno satellite, separated it from its Centaur stage after injecting it into a solar orbit that will hopefully swing around and go past the Earth, where we can get a gravity slingshot, but not before we do a deep space maneuver or two that will help our trajectory to make sure that we get that slingshot. And that's where we had left off. Now we'll pick it up from that point where we were waiting for the deep space maneuver to finish, and in the meantime head into the VAB to take a look at some of the construction. On the top of Juno, there are going to be various electrical components and science instruments and things like that I'm going to want to simulate having wires run to. So I have three different types of wire here. I have short, medium, and long. And I'll be using those in combinations to fill the top of this to just give it a little bit more realistic look. For now, the positions are going to look fairly random, but as I put more science instruments in on the top, they will start to make more sense and look like they're connecting various things together. Before we do the last science instruments, let's take a look at the last bits of the communications, propulsions, and orientations. For communication, we have right here the Juno medium gain antenna and forward low gain antenna. That is a few welded pieces that I put all together into this one arm that goes down here on the side of the electronics vault, something like that. You can see up close here that it's made up of some stretched cubic struts, as well as an antenna right there, a little dish that I miniaturized, and some little hoops on the end of this other antenna. We also have the RCS we need to put on up here. We have the top Juno RCS. These were particularly difficult to figure out what they were supposed to be, so there's a lot of guesswork going into this one, but you can see that this operates on hydrazine and has a fairly low thruster power, but that doesn't matter because they have all day long to rotate into the correct orientation when they're out there. I believe it has 3 nozzles, and these attach one on each side of the upper structure here. We have the long one that comes up like this, and this is made out of a tube that I elongated and put a little block on the end of it for the 3 nozzles to come out from there. That's all welded together, and then a copy of that gets taken, flipped around, and put on this side right over here. On the bottom side, we have the same idea. We have this little one that's the same thing, but just a little bit longer, a little shorter tube right there. Flip that one upside down and stick one copy there, and then copy that and put one on the other side as well. Just like that right there. To orient itself, we have to have a star compass. So the Juno Advanced Stellar Compass right here comes up and goes right in this location. We just have to rotate it into the correct orientation to have it right here, pointing out and watching the stars to make sure we know where we are at all times. We have this toroidal low gain antenna. We take that one and we put that down here on the bottom right about there. And we have the aft low gain antenna, and that one goes right in here. The basic structure of the satellite is complete, so now we just have science instruments to place around the outside of it. We'll take a look at one more of those right now and then go check on Juno out in orbit. This time we're going to look at the Juno MWR, the microwave radiometer. I welded these together using some LLL panels with some squad panels and just repeated a pattern over and over again to create different sizes. So we have this extra large one right here, which would take up an entire side. We have just a large one that would take up only a portion of a side. Then there's medium, which would go somewhere right around here. Small, which would go underneath it, and very small goes up here right on the edge, right about there. After shifting them around to be in the exact right positions, they would look something like this. 4 on this side right here, and then the large one over here, sticking down a little bit over the edge, both on that side and on this side, and this one's sticking up off the top.
NASA loves acronyms, and so I just simply abbreviated microwave radiometer as MWR. From its name, it measures the radiation in the microwave region. Now that sounds like, a lot of highfalutin scientific terms, but it's really pretty simple. What we're actually doing is measuring the thermal radiation from the atmosphere of Jupiter beneath the clouds. And at every wavelength, we have 6 wavelengths on the instrument. Every wavelength is designed to look at a different region of the atmosphere, measure the thermal radiation coming up from some different region in the atmosphere. And by measuring them with the spacecraft, we'll be able to put that together into a picture, a three-dimensional picture of the atmospheric structure of Jupiter. What we've come up with as the most effective way to build an antenna is a big flat array that's about 5 feet square all the way around. It's as big as the side of a spacecraft, which is not a coincidence because we sort of sized the spacecraft to hold an antenna for our longest wavelength. Now, the other wavelengths are progressively smaller by factors of 2 at every step. So it turns out another side of the spacecraft can hold all of the rest. So we have no idea what we're going to see because nobody's ever seen this region before. So it's going to be a surprise to all of us when we get the information back. So we expect to discover all sorts of new things.
Our Lyros 1B is still plugging away, doing its 635 or so newtons. The thrust range on that is anywhere from 587 to 707, but we're not going to be running it at full power. Anyway, the first 30 minutes are just about up, and at that point we can set up a maneuver node that will put us on a trajectory to do that flyby 2 weeks from now. Well, the Deep Space Maneuver number 2 is 2 weeks from now, but the flyby itself will be in another year. You can see the path right there that we're hoping to take after Deep Space Maneuver number 2, and if all works out correctly, notice over here we'll be making a Jupiter intercept. We'll put another science instrument on Juno here, although while we're at it, notice I have this tiny MWR sensor that was supposed to go right here. We didn't put that one on last time, so we'll get that one right now. It goes right next to this one right here, which was our very small. This one is our tiny sensor. While we're here, we should also finish off this other instrument. The magnetometer has this SHM, the Scalar Helium Magnetometer. It's an extra little bit that was an independent science instrument that goes right down on there. But the one we're really going to add this time is going to be this UVS, the Ultraviolet Imaging Spectrograph. Once again, that is a couple welded bits, and those are going to go over here. Notice that this has a large part to it that sticks up right there, but when I put it on the side of the craft, it kind of embeds itself so that you can only see the sensor, and the electronics box stays on the inside.
UVS stands for Ultraviolet Spectrograph. It's an instrument that looks at ultraviolet light you can't see with your eyes. It's too short a wavelength, but it also breaks that light up into different colors, much like a prism would break up white light into a rainbow. It has 2 components to it, actually. One is the sensor, which is sort of a telescope plus a spectrograph side by side. And all the electronics, except what need to be right at the sensor, are put in another box, which is deep inside a vault, which on Juno protects all the sensitive electronics from the radiation at Jupiter. Jupiter has some similarity to Earth. The Earth has northern lights, auroras, and they're spectacular to watch. Jupiter's auroras are like 1,000 times bigger. So the auroral oval on Jupiter is bigger than the entire Earth and much, much more powerful. And it's always on, but it's much easier to look at it in ultraviolet wavelengths because we can see it on the day side as well. When we see light from those different colors in the UV, they tell us different things about Jupiter's upper atmosphere and the particles that are causing the auroras to happen. We'll be able to contrast how auroras work at Earth with how they work at Jupiter. And there are many differences we already know, but there's a lot of things we've never been able to see at Jupiter that we can see with Juno once we get there.
We'll jump ahead 2 weeks now, and it's time for the second deep space maneuver. We're opening up the shield on the Lyros 1B, firing it up to about 90-95% of our thrust capacity, and beginning our second 30-minute-long maneuver. Like before, I set up the maneuver, went away for about 25 minutes, and came back later, watched the last 5 of it, and refined my approach in toward Jupiter. While we're over here on this side of Juno, let's finish off with the other instrument that goes right by the UVS here. It's the Juno cam. This one is composed of an actual camera from the Hullcam VDS mod, which was welded on top of a structure piece that connected to an Oscar fuel tank, shrunk down to be really small, then another inverted structure piece, and then a little block from Lackluster Labs. Altogether, when we take that, it sits embedded inside the craft like this. So only the camera sticks out, and the rest of the instruments are all inside that panel. If I bring it up toward the top here, you can see how it fits in there. Most of it is sunk inside, with just the tip of it showing right there next to the other science instrument.
JunoCam is on the spacecraft to take pictures of Jupiter, and we specifically designed it to get pictures of the polar regions of Jupiter. We've had a number of spacecraft that have flown past Jupiter and taken pictures, taken movies, but they've always been in the equatorial plane. And so this mission is the first one that we really get up over the polar regions. Let me mention that all of our pictures are of the cloud tops. Jupiter is a ball of gas, and all we will see are clouds. But they're very interesting, very dynamic clouds, so it should be fun. JunoCam is a unique element of the payload on this spacecraft because from the outset, its reason for being on the payload was to do outreach to the public. We do not have enough data volume to take a picture on every spin. We are going to have to be choosy and select what are the places that we want to take pictures of. We are going to invite the amateur astronomy community to send us their best data. So approximately a month away from when we take our data, we will be collecting the pictures from the amateur astronomy community and talk about why they would take a picture in any given latitude. And so the whole theme is to do science in a fishbowl. Let's do what we would do, but let's do it in a public forum so that the public can participate. And I'll be very happy if everybody gets involved the way I hope they do.
Zooming in here, we can see how our path is going to be crossing Earth's path, picking up that extra velocity, and then zooming out, we can now see how that gravity assist is helping us up toward Jupiter. And there it is, the Jupiter intercept. Dun, 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 dun. Now we can close up our Lyros engine. We won't be needing that anymore. And we can begin our 1-year-long journey back to where we started from, back to Earth. Except this time we're going to be getting something else once we're there again. That fabulous extra couple thousand meters per second of delta V. Our next instrument is going to be called the Juno Jedi. We need to place 3 of those. One of them will go over here. Another goes on its side at a different point, as if in a triangle over here on this corner of the surface of the craft. And then the last one will go normal side up, looking off of this last side.
It's the Jupiter Energetic Particle Detector Instrument, and the acronym does not quite work out properly, but somebody loved the word Jedi for obvious reasons. We affectionately call our instrument the hockey puck because the main sensor is about the size and shape of a hockey puck disc. That hockey puck is sort of glued on or attached to a box which holds all the electronics associated with the sensor. JADE in particular works in very close coordination with JEDI. So JADE is measuring the lower energy part of the charged particles that are in Jupiter's environment. JEDI measures the higher energy particles. Those particles then go through the instrument and strike what's called a microchannel plate sensor. And a microchannel plate sensor amplifies the signal so that you get a current out the back end, and modern electronics can measure electric currents. We measure the radiation belts around planets. All the strongly magnetized planets have radiation belts. Jupiter has the most intense and interesting radiation belts. It's a rotationally dominated space environment or magnetosphere, where Earth is a solar wind-driven space environment. By studying two different environments that are powered by different things, you can begin to isolate the physical processes that are causing these variations. We hope to make great discoveries there.
Well, he just talked about the JEDI instrument and JADE, but we haven't covered JADE, so we'll do that in just a moment, because as you see here, we're still making our 1-year loop around, getting ready for that gravity assist going past Earth. In the case of JADE, I once again welded multiple pieces together, but shrunk them down super small to make them look like a science instrument. Our hamster wheel sort of instrument will go over here, and then we have 3 JADE instruments that are going to look out the 3 different sides of Juno. So we'll place one right here, and one right here, and one right here.
JADE, the Jovian Auroral Dynamics Experiment, is a set of instruments that measures the electrons and ions. Those are particles, very tiny charged particles that are parts of an atom. And those particles actually produce the aurora. They follow along the magnetic field lines and they come down into the atmosphere at Jupiter, and they excite different sorts of interactions that emit light, different wavelengths of light. Those we observe as the aurora, but the aurora is really caused by these tiny, tiny particles coming down into the atmosphere. And JADE actually measures those individual particles. There are 3 identical electron sensors, and they look off in 3 different directions around the belly band of the spacecraft, so that they've got a broad field of view, 120 degrees wide, so the 3 of them actually can see all the way around the spacecraft all the time. The JADE ion instrument is different. It actually has a thing that looks a little bit more like a hamster wheel and a hamster cage, and that's to allow particles to come in over 270 degrees of observing angle, and twice per minute the Juno spacecraft spins around, and that allows that field of view to observe all of space. And so we're trying to understand what's the same and different between our own aurora and the aurora at Jupiter so that we can understand the processes really in detail for the first time. We'll be fully successful when we can come back and tell the world how it really works, what particles are involved, and why.
Oh, it's time. You can see that teal solar orbit is getting shorter, and there we go. We have crossed over onto the brown. Now the teal orbit is going past Earth. It's time for our gravity assist slingshot maneuver past the Earth, picking up the delta V we need to head out to Jupiter, and sure enough, we go out to the map and we have been flung straight toward that gorgeous planet. We launched in 2011, now it's 2013, about 2 years later, and we're making our flyby. Our arrival at Jupiter is projected for July of 2016. We're targeting a polar orbit around Jupiter for a couple reasons. One, it gives us a really good look at the planet. We'll be looping around it 33 times, and each time getting a different look, alternating which science instruments we'll be using as we take our look through each one. Our other main reason is it'll help us avoid any long-term exposure to the high radiation generated from Jupiter. That radiation could damage our instruments. Even though we are protecting them in a vault, we are not immune. Everything outside the vault is vulnerable too. The insertion burn will go through the close approach to Jupiter. The engine will burn for about 30 minutes, capturing into a 107-day, very elliptical orbit. But this will allow us to save fuel by doing a period reduction burn later. About 7 to 8 days in, we'll do a little cleanup burn to make sure we're aligned correctly. Then when we're swinging back around again, we'll reduce the overall orbit down to just 11 days. No science will be done on these initial orbits. The first couple are just to check out all of our systems and make sure everything is ready for the real science orbits that will begin on the third time around. We'll need to make sure that all of the science instruments are ready to go since we're just about in the orbit. And there's one more we haven't covered yet, so let's take a look at it now. This is the GIRUM instrument. I'm going to put a little integrator box up here on top of the satellite where all the wires are coming together. And then down below, put the instrument itself, which is another hull cam, embedded in a lackluster brick.
A Jupiter infrared auroral mapper is an image spectrometer. At the beginning was meant for supporting auroral observations, to make images of aurora, and at the same time to look at the different view of the aurora. GIRUM is made of two pieces. One part of GIRUM is called the optical head, where is the sensitive part of the instrument that can focus the images like a camera. And there is another box, which is the main electronic. And we can take images in two different wavelengths. One is devoted to the auroral observations, and the other part of the detector, the imager, it's sensitive to the thermal emission of the planet. So at the same time, we can take these two pictures that are superimposed, one above the other one, for observing the aurora if it's present. The reason why we are not with all the other instruments, but we are on a side in the aft deck of the spacecraft, is because we entered the mission later. So there was no more room in the big place, in the place where all the other instruments are. So we had to run quite fast to keep the pace with the mission.
We have almost finished our 30-minute long 107-day capture orbit burn. After that, as I mentioned earlier, we'll do some systems checks and then we'll swing around, go through that close approach one more time, bringing down to that 11-day orbit. And then for orbits 3 through 33, we're going to do different types of science for the next year. Every time through, we're going to spin around to make sure the craft is pointed the right direction to get all the science instruments where they need to be. Take our readings, and then as we leave, shifting back again so that the high-gain antenna can send that science back to Earth, capturing it with our 70-meter dish from the Deep Space Network. Each of the science orbits is only going to get to do some of the instruments as they go through. It's already been mapped out and planned exactly which orbits are going to be for which instruments. For the gravity science experiments, we need to have the high-gain antenna pointed at Earth so that we can compare data between Earth and the satellite. Most of the orbits are going to be for the gravity science, but some of them will allow the microwave radiometer to work. For that, the instruments need to be pointed at the planet, and that means the high-gain antenna will not be pointed at Earth, and therefore we cannot do the gravity experiments for those few orbits. But that's only a few of them. It's orbits 2, 4, 5, 6, and 7. All the rest of them are going to be gravity science orbits. Every other instrument can function regardless of how it's oriented, so we will get data from everything else no matter what. Then, ultimately, after a whole year going around Jupiter, after all the science has been collected, we will deorbit the spacecraft, sending it into Jupiter to be destroyed. We don't want it to accidentally collide with any of Jupiter's moons and contaminate it now, do we? So that will be the end of it then, on October 16th, 2017. It will all come to an end. And so that's it. Until next time, I will see you later, Kerbinauts.